We all know about the Large Hadron Collider at CERN, right? It's one of the most amazing things humanity has ever built. But what if I told you the universe is just filled with particle accelerators that make the LHC look like a complete toy? Seriously. So what are these cosmic powerhouses? Where are they? And how in the world do they work? Well, let's follow the clues and find out. Okay, let this sink in for a second. A particle, a single, tiny particle with the energy of a full-on LHC collision, hits every single square kilometer of Earth every single second. That means one just hits somewhere near you, and another one, and another. This isn't some rare freak event. It's a constant, invisible storm of high-energy particles raining down on us all the time. So the big question is, where are they all coming from? This bombardment has been going on for, billions of years. And for most of human history, we had absolutely no clue what was firing these cosmic bullets at us. It's truly one of the greatest detective stories in all of physics. All right, so to start cracking this case, we've got to go back over a century. And our story doesn't begin in some fancy state-of-the-art lab. Nope, it begins high up in the atmosphere. Back in 1912, this physicist, Victor Hess, he does something kind of crazy. He gets in a hot air balloon with some instruments to measure radiation. Now, everyone thought radiation would decrease the higher you got, right? Further from the Earth and all that. But Hess found the exact opposite. It got stronger. So he thinks, okay, maybe it's the sun. In a really clever move, he goes up again, at night. And then again during a solar eclipse, just to be sure. The result? Exactly the same. He realized something from the depths of space itself was bombarding us. He called them cosmic rays. And yeah, he totally won a Nobel Prize for it. So Hess figured out the what, that these rays exist. But the where they come from and the how they get so powerful, well, that stayed a mystery for pretty much 100 years. So let's jump ahead and look at the prime suspect. And here it is, the first big reveal. We now know that most of these cosmic rays come from one of the most violent events imaginable in the universe, an exploding star, a supernova. But that just opens up another can of worms, doesn't it? How does a big explosion manage to accelerate a tiny little particle to nearly the speed of light? That's the real puzzle. Well, it turns out the explosion itself isn't quite the whole story. The real secret sauce involves two key ingredients. You need supersonic shockwaves, and you need a whole mess of tangled up magnetic fields. Get those two things together, and you've got a cosmic accelerator. Okay, so how do these two things, shockwaves and magnetic fields, create a particle accelerator that's literally light years across? The whole mechanism is kind of like a giant game of cosmic ping pong. Seriously. Now, to really get what a shockwave is, let's start with a regular sound wave. Think of it as a pressure wave, right? The air molecules just kind of jiggle back and forth. But a shockwave, that's a whole different beast. It happens when whatever is making the disturbance is moving faster than sound. So instead of just nudging particles along, it violently slams into them, plowing through and creating this intense supersonic front. So when a massive star goes supernova, its outer layers get blasted out at like a few % of the speed of light. That is way, way faster than the speed of sound in the super thin gas of interstellar space. And what you get is this absolutely colossal expanding shockwave. But hold on a second. Space is mostly empty, right? So how does a shockwave even travel if there's nothing for the particles to bump into? The answer is magnetism. The shockwave uses these tangled magnetic fields almost like a giant net. It just grabs and sweeps up all the interstellar gas, the plasma, that's in front of it. It's pretty amazing. And this right here is where the magic happens, is a process called Fermi acceleration. So picture this. You've got a proton, just one little proton, and it gets caught right at the edge of this shockwave. It gets whacked by the messy magnetic fields behind the shock, and boom, it gets a little energy boost. That kick sends it flying across the shock front. Then it hits the magnetic fields ahead of the shock, gets whacked back across, and gains even more energy. It's this insane game of cosmic ping pong, bouncing back and forth, gaining speed with every single hit. This comparison really shows you why a supernova is just so incredibly powerful. See, at the LHC, they need these ridiculously strong magnets to bend the particles into a tight little 27-kilometer circle. A supernova remnant, its magnetic fields are way weaker, but its playground is light years across.
That means the particle's turning circle, what physicists call its Larmor radius, is basically unlimited. It has this enormous space to just keep accelerating to energies we can barely comprehend.
So, there we have it. Mystery solved, right? Supernovae make cosmic rays. Case closed. Well, not so fast. It turns out they don't make all of them. Just when you think you've got it all figured out, the universe loves to throw you a good old-fashioned curveball.
Yeah, there's a limit, a cap, if you will. From everything we can calculate, a typical supernova just can't accelerate a particle beyond about 10 to the 17th electron volts. Now, an electron volt, or EV, is a tiny unit of energy, but 10 to the 17th of them is an insane amount. But as huge as that number is, it's not the end of the story. Not even close. And that's because we've actually detected cosmic rays with energies 1,000 times higher than what a supernova can possibly turn out. I mean, look at this gap. The difference between the max supernova energy and the highest energy we've ever seen is just, it's enormous. So that means something else, something way, way bigger, has to be out there making these things. To give you some perspective on this, get this. The most energetic particle ever detected, and it has the best nickname, the oh my god particle, was a single subatomic nucleus, and it had the same kinetic energy as a baseball being thrown at almost 100 kilometers an hour. Think about that, a single invisible proton with the punch of a major league fastball. Supernova? They just can't do that. No way.
So this forces us to go hunting for even bigger, badder accelerators. The hunt is officially on for the true heavyweights of the universe.
And we've got a huge clue thanks to data from these massive detector arrays, like the Pierre Auger Observatory down in Argentina. When they map where these ultra-high-energy particles are coming from, their arrival directions don't line up with our own Milky Way galaxy. Not at all. They're extragalactic. They're coming from somewhere else entirely. So the question is, what out there is powerful enough to do this? The list of suspects, honestly, it reads like a cosmic most wanted poster. We're talking about things like the insane jets of plasma that get fired out of supermassive black holes, entire galaxies smashing into each other, hypernova, which are like supernova on steroids, and these ultramagnetic neutron stars called magnetars, the biggest, most violent stuff in the universe. And here's the really cool part. The underlying physics is probably the exact same thing we just talked about. These absolutely colossal events, they create shockwaves and tangled magnetic fields, just like a supernova, but on a scale that is just mind-boggling. So instead of a cosmic ping-pong game that's a few light years across, you're talking about one that spans hundreds of thousands of light years. It's the same engine, just massively supercharged. So think about this journey. We've gone from a mysterious rain of invisible particles to hunting down galactic-scale superaccelerators that are powered by things like colliding galaxies and monster black holes. These cosmic rays aren't just random particles. They're messengers from the most violent corners of the universe, and they're carrying secrets about space, time, and the very fabric of reality. So the question isn't just where do they come from anymore. The real question is, what amazing secrets will they tell us once we finally learn how to read their messages?